fooling the robots. All right. The discrete-time Kalman filter. So in some respects, this should have been the first lecture because the discrete-time Kalman filter is kind of the basis and the starting point for this whole field of using state-space models for doing signal processing and tracking and estimation. And a lot of what we're going to be talking about from this point in the term forward, as we talk about the incentive Kalman filter, other tools that can be used for nonlinear techniques, they're all based on the Kalman filter. And there are mashups with the particle filters that are really cool, where they use the Kalman filter and particle filters and blend them together in a really nice way. So don't think of this as like something that I'm teaching you, but why on earth would anyone ever use a Kalman filter these days? It's limited to linear state-space models, because this is still the basis of doing really clever, cool things, even with nonlinear models. So this is still important. You should still pay attention, not just because this kicked the whole field off and that history is interesting, but because these equations are still used very widely, even in nonlinear cases that come up a lot more often. So here's just an overview. I've got a few different examples that are new that I'll go through slowly, so I won't be doing the car tracking. You'll be glad to know.
I was curious how I was going to handle that bimodal bit.
Yeah, well, I could fold in the car if you want it.
I'm actually really curious.
Okay. You guys are giving me homework this time. That's okay. So, again, this is, I already said some of this, but the discrete time Kalman filter, it's limited to linear systems, so we're going to step into the linear world. It can still be time varying. There's still a lot of advantages, but it's going to be linear for a while. And there's other kind of bad things about the Kalman filter, but there's a lot of good. There's good reasons to really understand this thoroughly. Like one of my key learning objectives for all of you by the time you leave this class is to know how to drive a Kalman filter. So today, this set of slides is mostly about the math and getting to the optimal Kalman filter recursions. But the real value in having the Kalman filter and knowing it is knowing how to actually apply it to real problems. And knowing what its wrinkles are and how to kind of coax it to do the right thing, knowing how to tune it. And a lot of those ideas can be applied to the other algorithms that we're talking about, including the particle filters. So there's a lot here, and I'll be expanding these notes the next time we talk about this. So here are some of the advantages. It is computationally efficient. Particle filters are kind of like Moore's law is here. Just throw a bunch of cycles at it, and with the law of large numbers, things will work out. And you've seen that in simple cases, that it actually works. And today, in 2016, computation is so cheap that, why would you ever bother with a Kalman filter? But it turns out there are good reasons. Moore's law loses in the race with the curse of dimensionality, and Kalman filters win. So this is computationally efficient, way more than particle filters, and certainly way more than the Viterbi algorithm. Under certain conditions that are broader than what most people understand, it's optimal. And I'll say more about that. The book does a good job drawing a distinction between what a lot of people understand and how broad of case this is actually optimal. It provides a lot of really critical insights in working with state-space models, especially those of you that have a controls background or are working on controls problems. It's really good to understand what the Kalman filter tells you about linear state-space models. It's the foundation of state-space methods, so there is the heritage aspect. And it does help us also better understand some of the things we should be asking of any state-space tracking algorithm, because the Kalman filter gives us a lot. Particle filters give us a heck of a lot too, but it's good to know what questions you should be asking when someone gets up and presents a design of a state-space tracking algorithm. It's used in a lot of different systems. It's been a very, very successful discovery or finding. So, linear state-space models. There's a lot of math in this set of slides, which if you've survived this long, you're not scared of. And let me say that I'm following the book pretty closely. My notation is a little bit different, and there are lots of different derivations of the Kalman filter recursions, and some are more general than others. Those of you with a controls background have already been asking me, in the process model, can we feed in external inputs and somehow have those affect the state also? Could we add a term, I think I can add this temporarily, where we have maybe plus a G in a time-varying matrix times maybe another input, U of n, that is feeding into this. And likewise, you could consider that you've got an external input going into your measurement model as well. Let's see, E, F, G, H, I, J. I'm running out of, I don't even know what to use. I guess I'll use E. I don't remember what's typically used, but maybe if your external input vector, you've got that also driving your measurement model. So there are derivations of the Kalman filter that are fairly straightforward that account for these terms also. But my goal is for you to understand where these recursions come from. And it's much easier to teach and to understand the first time if you consider a more limited case. So I'm not teaching the most general form of the Kalman filter. So when you look at this and you're like, well, wait a minute, I've got an external input, so shoot, I can't use a Kalman filter. It turns out it's not true. There's lots of ways to generalize and go beyond a lot of the restrictions that are here. So our state space model, we've got the state vector that you're familiar with at time n plus 1. And it's got dimension, I think I usually use m. We've got our state transition matrix, which is, again, can be time varying. Kalman filter just doesn't care. Time varying is no problem at all. We've got our state vector at time n. We've got additive process noise. It can have an arbitrary covariance matrix. And I'm only requiring that the sequence of process noise, that it be zero mean and uncorrelated. I mean, white basically just means that it's zero mean and uncorrelated. I'm not requiring that it be Gaussian. That's not necessary for any of the math or for the recursions. A lot of people think Kalman filter is only optimal when you've got Gaussian noise. It's not true. It's still optimal even if it's non-Gaussian in a certain sense that I'll explain later. So I'm assuming white noise, not necessarily Gaussian noise, but white noise. Similarly, for our measurement model, we've got our measurement vector, a vector of the measurements that usually come directly from the sensors. We've got the matrix that relates our state vector to our measurements. I forget the name of that matrix. It's probably the H matrix. Thank you. The what? Okay. And then we've got our measurement noise that is the vector Vn that has the same dimensions as Yn. And again, that can have an arbitrary covariance matrix. It doesn't matter what it is. Different elements of this vector can be correlated with itself. In this formulation, I am requiring, again, that it's uncorrelated. So it says white noise. It's kind of redundant with what I've got expressed here. But the covariance matrices between the process noise at time n and the process noise at time m is only non-zero when n is equal to m. Otherwise, it's 0. So this is the Kronecker delta function. So this is basically just another way of saying it's uncorrelated. I'm also assuming in this formulation, because it's a lot easier to derive, that there's no correlation between the measurement noise and the process noise. But when I learned this, poor me with learning this from Dr. Kailath, it didn't make this assumption, and so there is a way of formulating this where you don't have to make that assumption. There's a way to make that work. But in most applications, I think that's true. Okay, so that's this is the general formulation of the linear state space models we're going to be working with and coming up with these recursions. Colin, you look like you don't like that.
Sorry, I was just trying to think. Well, so for those expectations, we've got W and V. Those are they vectors?
Yeah, this is the expectation of an outer product.
Okay, so I was thinking, shouldn't the bottom one be W transpose V? If it just gives you a scalar.
These are different dimensions.
See, that's a zero vector.
Is that a zero?
Oh, that's a vector. Yeah,
Okay.
sorry. Thank you, Walt. That's absolutely right. This is a zero vector,
Zero.
and it's of dimension. Oh gosh, I haven't specified what I'm using for the dimensionality. This is going to be a little bit awkward, but I'll do it this way: in x by n, y. That's the dimension of the zero matrix. I said vector, I meant matrix. It's a matrix of zeros.
Now I see why people use K for time.
Oh, yeah, maybe. I think it makes things worse, but that's me. So any other questions about the model? No? It's okay? All right. So our goal with a Kalman filter, as with the particle filters, is to estimate the state at time n. Everything we just talked about with the Viterbi algorithm, forget it for this set of slides. There's no notion of a joint posterior here. It's only the marginal. So we're back to just thinking about, give me the best estimate of the state at time n. And the knowledge we have, as usual, we're in the Bayesian world. The thing we're trying to estimate is random. And we have both prior knowledge that is captured by the, I should probably write this out. This is going to be more trouble than it's worth, I can tell already. By the process model. And then we've got our measurement model that gives us the information from the measurement. So there's the idea of the prior knowledge in the process model. So this is where our prior knowledge is, and then this is the measurements. They're giving us basically data that give us information about our state. And the Kalman filter is able to combine the information from these two sources optimally to estimate the posterior mean. And again, we're looking at the marginal posterior, and this is most appropriate, of course, when your marginal posterior is unimodal. We're estimating a mean. That's the only thing the Kalman filter is going to give us, is an estimate of the mean and the covariance of that marginal posterior. So if it's multimodal, you're going to be blind. You won't be able to see that within this framework. And xn is going to be estimated as a linear combination of all the observations from time n to time n minus 1. So one way of expressing that is to say our estimate x hat of n is going to be equal to maybe some big, this is not the Kalman gain, but let's just say some appropriate big, huge matrix times kind of a collection of all the measurements. This is y0, y1, all the way down to something, maybe yn, for example. So our estimate of the state is going to be that way. And it turns out, the book doesn't show it. You can find it in courses that spend a lot more time on this, but it turns out that the linear combination is optimal. So it's the right thing to do depending on what your optimality criterion is. But if you're trying to minimize mean squared error, it turns out that a linear combination is the right thing. So one way of thinking about it is that we're trying to get an estimate of the state where we're taking a linear combination of all of the possible measurements. Of course, this will be done efficiently and computationally efficiently and recursively, but it's good to keep in mind. And it took me a long time to even believe this, much less, I should say, it took me a long time to understand it, and then an even longer time to believe it. But really what we're doing is the equivalent of figuring out an optimal matrix K that linear combines all this stuff, all your measurement vectors. So that is what it does. So again, just a little bit on the assumptions. Noise is white, but it doesn't have to be Gaussian. We're not assuming Gaussian noise. We're estimating the mean and the covariance, and we're assuming that that's an accurate enough characterization of the posterior, the marginal posterior, for our tracking application.
Does the noise have to be stationary, or can we have moments that are non-zero higher than the second moment?
It is. I was stuck on the first part of your question. We're not assuming that the noise is stationary. We're assuming it's uncorrelated, but it's not stationary because the covariance can change over time.
Yeah, obviously, yeah, because the covariance can change. Never mind. That makes sense. Like, can you have moments, can the white noise, or the noise be described with moments higher than just the first and second moments? Like, because I could think of a possible weird-looking PDF that has a mean of 0 and really bad kurtosis or something.
Yeah, I understand. The Kalman filter, it turns out, will minimize the mean squared error, and it doesn't pay any attention to those higher moments. So if you've got a heavily tailed distribution, if it's very non-Gaussian in that way, then be careful. Those outliers are going to kick it around. Minimizing mean squared error is a hazardous thing to do when you've got a heavy tailed distribution. Any other questions so far? Okay. So just a little bit of notational differences. I'm following the Simon text, and I created these slides to try to follow what Simon did closely. I'm finally back to kind of trying to follow the book pretty well, so you've got more than one source for the same information. But of course there are differences. As Andy already pointed out, I'm using N instead of K for the independent time index. I've been doing that throughout the class, and it's just a personal preference, and it's kind of how I learned the Kalman filters with N instead of K, so I'm kind of wedded to it now. So as an instructor, you get to make that kind of override choice. I'm also expressing the process, what I usually call the process model. Here I'm calling it the state model, but more appropriately the process model in terms of x of n plus 1 instead of x of n. You could, of course, write this, decrease the time indices all by 1 and have this be x of n is equal to f of n minus 1 times x of n minus 1, etc. And I'm not doing that. I'm going to do it this way because that's what I'm doing for everything else. And I think it's a little bit easier to understand it that way. I'm also using this bar notation to explain what observations we have. We always have the observations from time 0 to some other time, and this means we're estimating the state at time n given that we've seen all the measurements from 0 up to whatever time is indicated there. The book uses a pretty common notation for explaining the Kalman filter, where if it goes up to n, they use this plus superscript, and if it goes to n minus 1, they use this minus superscript. So when you read the text, you'll see that, or if you look at other references, you'll probably see that. As I mentioned, I didn't include the external input term to the state dynamics. You could. Turns out you can also add it to the measurement model, and it doesn't change things a whole lot. It's a pretty small thing to have to do. I'm also using the this norm notation, where I've got the two vertical bars. This indicates that there's a norm of some sort. And in this case, this norm basically means that I'm looking at a covariance matrix. And this is an expectation. This is not a calculation. So this is an expectation over whatever the distribution is of the state vector at time n. And I'll try to use consistently. I had to do a little bit of cleanup in preparing today, but I think I managed to make all of the random variables and vectors indicated in boldface. So that's the distinction that I'm using notationally. So the Kalman filter gives us two different estimates. One of the things it gives us is what's called an a posteriori estimate, or what I usually call a filtered estimate. So this is the expected value of the state vector given all the measurements from 1 to n. And I know usually I assume that your first measurement comes at time 0, but I'm following the book for this set of slides, and I'm assuming here that the first measurement comes at time 1 instead of at time 0. So there's a small difference there as well. The other thing is the a priori estimate, or what I usually call the filtered estimate, where you've got all the measurements up till time n minus 1, but you don't have the most recent measurement. And the Kalman filter goes back and forth between estimating those two as part of the algorithm. That's why they're so common.
Do you call both of them the filtered estimate?
I'm sorry, it's getting late, isn't it? So this one's predicted, this one's filtered. Filtered and predicted. I'm sorry if I misspoke. And both of these are estimates of the state at the same time at time n. It's just what they're conditioned on that is different. And I think that's probably a good stopping point for us. It's 6:26 and we didn't have a break today, so why don't we stop there? I look forward to your project presentations on Tuesday, and I'll give myself homework of having a closer look at that Viterbi example and folding the car tracking example into this set of slides.